All right, let's dive into something seriously cool today. Hydraulics. You've seen it, right? Big, powerful machines lifting tons of stuff. Or the brakes in your car bringing you to a safe stop. That's often hydraulics at work. And the secret sauce behind a lot of it is a principle called Pascal's law. It's named after Blaise Pascal, a pretty smart dude from way back in the 17th century. He figured out something amazing about fluids, and it's changed the way we build and move things ever since. From the jack that lifts your car to the massive arms of an excavator, Pascal's law is there, quietly doing its job. Understanding it is like getting a backstage pass to see how some of the world's most powerful machinery operates. It's a beautiful piece of science that has very practical, very powerful applications all around us every single day. So, what did Blaise Pascal actually figure out? Pascal's law states that an increase in pressure at any point in a confined fluid is transmitted equally throughout the fluid. Push on a fluid in one spot, and that pressure is felt everywhere. This principle makes hydraulic systems possible. Now, let's talk about the equation P equals Fa. P stands for pressure, F stands for force, and A stands for area. Pressure is the force divided by the area it's acting upon. This equation helps us manipulate forces using fluids. This is the mechanical advantage that hydraulic systems offer. Okay, theory is great, but let's see this in action with some numbers. Imagine we have a simple hydraulic system, two cylinders connected by a pipe, filled with an incompressible fluid, like oil. Piston 1, our input piston, has a small surface area of 2 square centimeters, cm2. Piston 2, our output piston, is much larger, with a surface area of 20 square centimeters, cm2. Suppose we push down on piston 1 with a force of 10 newtons. Using P equal Fa, we calculate the pressure exerted on the fluid by piston 1 10 newtons. 2 cm2 equaled 5 N cm2. This pressure is transmitted undiminished throughout the entire fluid. The fluid under piston 2 also experiences that exact same pressure of 5 N cm2. Now we can figure out the output force on piston 2, F2, equals P2, 20 cmt2, is 100 newtons. We pushed with 10 newtons and we got 100 newtons out. This is the power of hydraulics, all thanks to Pascal's law. This simple example shows exactly how hydraulic systems give us that incredible mechanical advantage. Section 4. Pascal in action. Real-world hydraulic heroes. One of the most common examples is hydraulic brakes in a car. When you press that brake pedal, you're actually pushing a small piston in the master cylinder, creating pressure in the brake fluid.
Thanks to Pascal's law, this pressure is transmitted equally through the brake lines to larger pistons at each wheel, creating the friction needed to slow down or stop your vehicle.
Then there are hydraulic lifts, like the ones in auto repair shops, hoisting cars high into the air. You pump a handle, which applies force to a small piston, building up pressure in the hydraulic fluid.
This pressure is then transmitted to a much larger piston, which is connected to the lifting platform, easily lifting incredibly heavy objects.
Hydraulic presses are another fantastic application, used in manufacturing for tasks like shaping metal sheets or compacting materials.
A pump generates high pressure in the hydraulic fluid, and this pressure acts on a large piston to produce colossal forces.
Think about heavy construction equipment, excavators, bulldozers, backhoes. Those powerful arms and buckets are moved by hydraulic rams.
Pascal's law is truly a workhorse principle, enabling countless technologies that shape our modern world by allowing us to control and multiply force with remarkable efficiency and precision.
Section 5. Hold your horses. The not-so-fine print. Assumptions and limits. Pascal's law operates under certain ideal conditions, or assumptions.
The first major assumption is that the fluid being used is incompressible. Most liquids, like oil or water, are pretty close to incompressible under typical hydraulic pressures.
Another important assumption is that the fluid is static or moving in a slow, steady flow without much turbulence.
When fluids start moving quickly, you can get energy losses due to friction within the fluid, known as viscosity and turbulence.
Engineers have to account for these dynamic effects in high-speed hydraulic systems.
There's friction between the fluid and the walls of the pipes and cylinders, and in the seals around the pistons.
Engineers work hard to minimize these frictional losses, but they can never be eliminated entirely.
Leaks mean that fluid, and therefore pressure, is lost from the system, reducing the efficiency and effectiveness of the hydraulic device.
So, while Pascal's law provides the powerful foundation, real-world engineering involves dealing with these practicalities to make systems work reliably and efficiently. Why Pascal's law rocks our world? Pascal's law tells us something beautifully simple. If you apply pressure to a fluid in a container, it spreads equally.
This idea, conceived centuries ago, is key in modern engineering. It allows force multiplication, lifting cars, and more.
It's how brakes stop tons of metal with foot pressure. Pascal's law harnesses fluid power, making life safer and productive. So, next time you see a backhoe or feel your car brake, nod to Pascal.